In 1929, an astronomer named Edwin Hubble made a discovery that would fundamentally change how we understand reality itself. He was studying distant galaxies, measuring their light, when he noticed something peculiar. The light from these galaxies was shifted toward the red end of the spectrum, and the farther away a galaxy was, the more its light was shifted. This red shift, as it came to be known, could only mean one thing. These galaxies were moving away from us. Not just a few of them, but all of them. And not just moving away slowly, but racing away at tremendous speeds. The farther away they were, the faster they were receding. Hubble had discovered that the universe itself was expanding. Now, when most people first hear this, they nod along. Sure, the universe is expanding, galaxies are moving apart, that makes sense. But then, usually within a few seconds, a question pops into their head. A question so obvious, so natural, that it seems almost childish not to ask it. If the universe is expanding, what is it expanding into? It's the kind of question that feels like it should have a straightforward answer. After all, when a balloon expands, it expands into the air around it. When a city expands, it expands into the surrounding countryside. When anything expands, it's always expanding into something, right? So, what about the universe? What's outside of it? What's the universe pushing into as it gets bigger? Here's where things get uncomfortable, because the answer isn't what you think. In fact, the answer is going to require us to completely rethink what we mean by words like space, expansion, and even existence itself. But before we get there, we need to understand why this question feels so natural to us in the first place, and why our intuition is leading us astray. You see, human brains evolved to understand a very specific type of environment. We evolved to navigate through three-dimensional space, to track objects as they move through that space, to understand relationships between things that exist within space. When you throw a ball, your brain automatically calculates its arc through space. When you walk through a doorway, your brain understands that you're moving through space. Space, to us, is like a container. It's the stage on which everything happens. It's always been there, it always will be there, and things move around within it. This understanding of space is so deeply embedded in how we think that it's almost impossible to conceptualize it any other way. So, when we hear that the universe is expanding, our brain immediately slots this into the only framework it knows. The universe must be like a ball of stuff expanding outward into some larger container, some bigger space that exists around it. It's not your fault for thinking this way. It's not anyone's fault. This is how human cognition works. We understand objects in space, not space itself. But here's the problem. The universe isn't an object in space. The universe is space. And that changes everything. To understand why, we need to take a journey through the history of how humanity has thought about space and the cosmos. Because this question, what is the universe expanding into, is actually a very old question in disguise. It's been asked in different ways, in different eras, by different people, and the answers have evolved as our understanding has deepened. Let's start with the ancient world. For most of human history, the cosmos was thought to be finite. The Greeks imagined a sphere of stars surrounding the Earth, beyond which there was simply nothing. Not empty space, but literally nothing. No space, no time, no existence of any kind. Aristotle argued that the universe couldn't be infinite because infinity was impossible to comprehend, and nature wouldn't create something incomprehensible. This view dominated Western thought for nearly 2,000 years. The universe was a bubble of existence floating in an ocean of non-existence. But then, during the scientific revolution, people started questioning this idea. If the universe has an edge, what happens if you go to that edge and stick your hand through? Does your hand disappear? Does it hit a wall? And if it hits a wall, what's the wall made of? And what's on the other side of the wall? These questions led some thinkers, like Giordano Bruno, to propose that the universe must be infinite. There is no edge, no boundary, no outside. The stars go on forever in all directions. Bruno was burned at the stake for this and other heresies in 1600, but his idea lingered. By the time Isaac Newton came along in the late 1600s, the infinite universe had become the prevailing view among scientists. Newton's laws of motion and gravity seemed to require an infinite universe. If the universe were finite, gravity would cause all the matter to collapse inward toward the center. But if the universe were infinite, with matter spread evenly throughout, there would be no center for everything to collapse toward. Every point would be pulling equally in all directions. The universe would be static, eternal, and infinite. And for about 200 years, that's what scientists believed. But there was a problem with Newton's infinite universe, and it was a problem that wouldn't be fully appreciated until the early 20th century. In an infinite universe filled with stars, the night sky should be blindingly bright. Think about it. No matter which direction you look, your line of sight should eventually hit a star. It might be a very distant star, but it's there. With infinite stars in infinite space, the entire sky should be covered in starlight. This puzzle, known as Olber's paradox, suggested that something was wrong with the infinite static universe model. Enter Albert Einstein. In 1915, Einstein published his theory of general relativity, and it completely revolutionized our understanding of space, time, and gravity. Einstein showed that space and time aren't separate things. They're woven together into a single fabric called space-time. And this fabric isn't just a passive stage where things happen, it's dynamic. It can bend, warp, and curve in response to matter and energy. What we call gravity isn't a force pulling objects together. It's objects following the curved contours of space-time. A planet orbits a star not because the star is pulling on it, but because the star's mass curves the space-time around it, and the planet is simply moving along the straightest possible path through that curved space-time. This was a radical departure from Newton's view of space as an absolute, unchanging background. But even Einstein wasn't ready to fully embrace the implications of his own theory. When he applied his equations to the universe as a whole, he found something disturbing. His equations predicted that the universe should either be expanding or contracting. It couldn't be static. But Einstein, like everyone else at the time, believed the universe was static and eternal. So he did something he would later call his biggest blunder. He added a term to his equations called the cosmological constant that would allow for a static universe. It was a fudge factor, essentially, a mathematical trick to make the equations give the answer he wanted. But then came 1929, and Hubble's discovery. The universe wasn't static at all. It was expanding. And not only that, but it was expanding in a very specific way. The farther away a galaxy was, the faster it was moving away. This relationship, now called Hubble's law, had a profound implication. If you ran the clock backward, if you imagined the expansion happening in reverse, all the galaxies would get closer and closer together. And if you went back far enough, everything in the universe would be compressed into an infinitesimally small point. The universe had a beginning. This idea was initially met with skepticism and even mockery. The astronomer Fred Hoyle derisively called it the Big Bang, a name that stuck even though it's somewhat misleading. It wasn't an explosion in space. It was an explosion of space itself. But we're getting ahead of ourselves. Let's get back to the question at hand. If the universe is expanding, what's it expanding into? Now that we know the universe had a beginning, now that we know it's been expanding for nearly 14 billion years, surely we can answer this question. Surely there must be some kind of space or void or something that the universe is expanding into. But here's where we need to pause and really think about what we mean by the word space. Because the answer to our question hinges entirely on understanding what space actually is. Before Einstein, space was thought of as a kind of fixed grid, a three-dimensional coordinate system that existed independently of anything in it. You could remove all the matter, all the energy, everything, and space would still be there. An empty framework. Absolute space. But Einstein showed us that this view is wrong. Space doesn't exist independently of the things in it. Space is defined by the relationships between things. More precisely, space is the geometry of possible relationships between events. Without matter and energy, there's no space-time at all. Not empty space-time, but no space-time. This is a crucial point, and it's worth repeating because it's so counterintuitive. Space isn't a thing. It's not made of anything. It's a mathematical description of how events and objects relate to each other. When we say two galaxies are 1,000,000 light-years apart, we're not saying there's 1,000,000 light-years worth of stuff called space between them. We're saying that light takes 1,000,000 years to travel from one to the other. We're describing a relationship, not a substance. So when the universe expands, what's really happening? Are the galaxies moving through space like cars on a highway? No. Space itself is expanding. The relationships between distant objects are changing. The amount of space-time between them is increasing. It's not that there's more space being added from somewhere else. It's that the geometry is changing. Think of it this way. Imagine you have a grid drawn on a rubber sheet. You place some coins on the grid at various intersections. Now, if you stretch the rubber sheet, the coins move farther apart. But the coins aren't sliding across the sheet. The sheet itself is expanding, carrying the coins with it. More importantly, there's nothing outside the sheet that it's expanding into. The sheet is all there is. If you're an ant living on that sheet, you have no concept of off the sheet. There is no off the sheet in your reality. The sheet is your entire universe. Now, this analogy breaks down because we're imagining the rubber sheet embedded in three-dimensional space, and we can see it from outside. But the real universe isn't embedded in anything. There's no outside. There is no higher dimensional space that the universe sits in. The universe is all of space. When space expands, it's not pushing into anything. It's just expanding. The distances between things are getting larger, but there's no edge advancing into a void. So why do we have such a hard time wrapping our heads around this? Why does it feel like there must be something outside? It's because of that same evolutionary baggage we talked about earlier. Our brains are wired to understand objects in space, not space itself. We can't help but imagine the universe as an object, a thing, a bubble of existence. And bubbles, in our experience, always have an inside and an outside. But the universe isn't a bubble floating in something larger. It's the only thing there is. Asking what's outside the universe is like asking what's north of the North Pole. The question seems to make grammatical sense, but it's actually meaningless. North is defined as a direction on the surface of the Earth toward the North Pole. Once you're at the North Pole, there is no north. The concept doesn't apply anymore. Similarly, outside is defined as a region of space beyond a boundary. But if the universe is all of space, there is no beyond. The concept doesn't apply. Now, I know what you're thinking. This is deeply unsatisfying. It feels like a cop-out. It feels like we're just dodging the question with wordplay. But it's not wordplay. It's a genuine consequence of how space and the universe actually work according to our best scientific understanding. And if it helps, you're not alone in finding this frustrating. Professional physicists and cosmologists struggle with this too. Some of the greatest minds in science have tied themselves in knots trying to make sense of it. Even Einstein initially resisted some of the implications of his own equations. The idea that the universe could be expanding seemed absurd to him at first. So let's take a step back and approach this from a different angle. Maybe the question isn't what is the universe expanding into, but rather, could the universe have an edge? Could there be a boundary beyond which there's nothing? And if so, what would that look like? This brings us to one of the most profound questions in cosmology. What is the shape of the universe? And to answer that, we're going to need to talk about geometry, infinity, and the strange topology of space itself. But that's a journey for the next part of our story. The shape of the universe. It sounds like a simple question, but it's one that touches on some of the deepest mysteries in all of cosmology. When we ask what shape the universe has, we're not asking whether it's a sphere or a cube or some other familiar three-dimensional object. We're asking about the geometry of space itself. And depending on the answer, the question of what the universe is expanding into might have very different implications. Let's start with something familiar: the surface of the Earth. If you stand on the ground and look around, the Earth looks flat. You can walk in any direction and you never seem to reach an edge. But we know the Earth isn't actually flat. It's a sphere. The surface is curved in a way that's hard to perceive when you're standing on it, but it's there. Now, here's the interesting part. The surface of a sphere is finite but has no boundary. If you start walking in one direction and keep going, you'll eventually come back to where you started. You'll never reach an edge because there is no edge. The surface just curves back on itself. But notice something crucial. We're only talking about the two-dimensional surface of the sphere. The sphere itself exists in three-dimensional space. We can see it from the outside, floating in space, curving through that third dimension. But if you were a two-dimensional creature living on that surface, you would have no awareness of the third dimension. You couldn't point to it or move through it. To you, the surface would be your entire universe, and that universe would be finite, curved, and without boundary. But you'd have no concept of what it's curving through. This is analogous to one possible shape for our universe. Our universe could be the three-dimensional surface of a four-dimensional hypersphere. Just as a sphere's surface is two-dimensional, but curves through three dimensions, a hypersphere's surface is three-dimensional, but curves through four dimensions. And just like the creature on the sphere's surface, we have no direct awareness of that fourth dimension. We can't point to it. We can't move through it. But mathematically, it could be there. If the universe has this shape, which cosmologists call positive curvature or a closed universe, then it's finite but unbounded. There's a limited amount of space, but no edge. If you traveled in one direction long enough, you'd eventually come back to where you started. And here's the kicker. If this is the shape of our universe, then, in some sense, yes, the universe is expanding into something. It's expanding into that higher dimensional space. The hypersphere is getting bigger, just like a balloon being inflated. But, and this is important, we can never access that higher dimension. It's not part of our universe. It's not somewhere we could ever go or observe or interact with in any way. So, even in this scenario, from our perspective, trapped in three-dimensional space, there's still no outside to the universe. But a closed universe isn't the only possibility. There's another option. A flat universe. Imagine you're standing on an infinite plane. Not a sphere, but a perfectly flat surface that extends forever in all directions. This surface also has no edge, not because it curves back on itself, but because it just keeps going. Forever. If you start walking in one direction, you'll never come back to where you started. You'll just keep walking forever, always finding more surface ahead of you. This is a flat universe. The geometry is Euclidean, meaning all the rules you learned in high school geometry apply. Parallel lines stay parallel forever. The angles in a triangle add up to exactly 180 degrees. The circumference of a circle is exactly 2 pi times its radius. And, unlike the closed universe, a flat universe doesn't need to be embedded in a higher dimension. It can just exist on its own. An infinite, flat, three-dimensional space. If our universe is flat and infinite, then the expansion takes on a very different character. The universe isn't getting bigger in the sense of increasing its total size because it was already infinitely large. Instead, the expansion means that the density is decreasing. The amount of space between any two distant points is increasing, but the total amount of space was always infinite, and still is infinite. There's a strange property of infinity that makes this possible. Infinity isn't a number, it's a concept. And there are different ways for something to be infinite. An infinite universe that's expanding is still infinite, but it's a different kind of infinite than it was before. The distances between things are larger, but the total extent is still boundless. Then there's a third possibility, a hyperbolic universe, or a universe with negative curvature. This one is harder to visualize because we don't have good everyday analogies for it. But imagine a saddle shape. At any point on a saddle, the surface curves up in one direction and down in another direction. That's negative curvature. A hyperbolic universe is like that, but in 3 dimensions. The geometry is strange. Parallel lines diverge from each other. The angles in a triangle add up to less than 180 degrees. The circumference of a circle is more than 2 pi times its radius. And, like a flat universe, a hyperbolic universe is infinite. It goes on forever, never curving back on itself. So we have 3 possibilities. A closed universe that's finite and curves back on itself. A flat universe that's infinite and Euclidean. And a hyperbolic universe that's infinite and saddle-shaped. Which one do we live in? This is one of the most important questions in cosmology, and for decades, scientists have been trying to answer it. The way to determine the shape of the universe is to measure its curvature. And the way to measure curvature is to look at very large-scale structures and see if they behave the way you'd expect in flat space, or if there are deviations. One method involves looking at the cosmic microwave background. This is the light left over from the Big Bang, the earliest light we can possibly observe. It was emitted when the universe was only about 380,000 years old, and it's been traveling through space ever since, red-shifted by the expansion into the microwave part of the spectrum. This light has tiny temperature fluctuations in it, hot spots and cold spots that represent the seeds of all the galaxies and structures we see today. By measuring the size and distribution of these fluctuations, we can infer the geometry of space. If space is flat, the fluctuations should have a certain angular size on the sky. If space is curved, they'd appear larger or smaller depending on whether the curvature is positive or negative. 2 satellites have made extremely precise measurements of the cosmic microwave background. The first was WMAP, the Wilkinson Microwave Anisotropy Probe, which operated from 2001 to 2010. The second was Planck, a European Space Agency mission that ran from 2009 to 2013. Both satellites measured the cosmic microwave background to extraordinary precision. And their conclusion? The universe is flat. Or at least, it's flat to within the measurement error. If there's any curvature at all, it's so slight that we can't detect it with current technology. Now, this doesn't prove the universe is perfectly flat. It's possible there's a tiny amount of curvature that we just can't measure yet. But the data strongly suggests that if the universe is curved, the curvature is extremely small. So, what does this mean for our question about what the universe is expanding into? If the universe is flat, and current evidence suggests it is, then it's almost certainly infinite. And if it's infinite, then the whole concept of expanding into something becomes meaningless. An infinite universe doesn't have an edge advancing into anything. It's just infinite space with the density of matter and energy decreasing over time. But wait, you might be thinking, if the universe is infinite now, how could it have started from a single point at the Big Bang? Doesn't an infinite universe mean it was always infinite? This is where things get really mind-bending. Yes, if the universe is infinite now, it was always infinite, even at the moment of the Big Bang. I know that sounds contradictory. How can an infinite universe come from a point? But the Big Bang wasn't a point in space. It was a point in time. Or more accurately, it was a moment when the density and temperature of the universe were infinitely high everywhere. Let me try to explain this more carefully. When we rewind the clock on the universe's expansion, we're not watching some finite ball of matter shrink down to a point. We're watching the entire infinite universe become more and more dense, hotter and hotter, until we reach a moment where the density becomes infinite. This is the Big Bang. Every point in space was arbitrarily close to every other point, but there were still infinitely many points. It's hard to wrap your head around because we're dealing with infinities in strange ways. But mathematically, it's consistent. An infinite universe can expand from an initial state of infinite density. The key insight is that the Big Bang didn't happen at a location. It happened at all locations simultaneously. Every point in the universe was part of the Big Bang. There's no center. There's no special location where it all started. If you could somehow rewind time and watch the universe contract, you wouldn't see everything collapsing toward some central point. You'd see everything getting closer together everywhere, uniformly, throughout all of infinite space. Another way to think about it is this. The Big Bang wasn't the beginning of space. Space already existed, possibly infinitely. The Big Bang was the beginning of the expansion. It was the moment when space started getting less dense, when the distances between things started increasing. But space itself, the stage on which all this happens, may have always been infinite. Now, there's something important we need to address here. When we talk about the universe, we need to distinguish between two different concepts: the observable universe and the entire universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old, you might think the observable universe has a radius of 13.8 billion light-years. But because the universe has been expanding this whole time, the actual radius is larger, about 46.5 billion light-years. This is the edge of what we can see. Not because there's nothing beyond it, but because light from beyond that distance hasn't had time to reach us yet. The observable universe is finite. It's a sphere centered on us with a radius of 46.5 billion light-years. But the entire universe, the totality of everything that exists, is likely much larger, possibly infinite. We can only see a tiny bubble of it. Think of it like being in the middle of an ocean. You can see to the horizon, maybe a few kilometers in every direction, but the ocean extends far beyond what you can see. The observable universe is our horizon, the cosmic horizon. Beyond it, there's more universe, probably a lot more, maybe infinitely more. And here's something that should blow your mind. If the universe is infinite, then there are infinitely many other observable universe-sized regions out there, completely disconnected from ours. Light from those regions will never reach us. We will never be able to see them, or communicate with them, or interact with them in any way. They're beyond our cosmic horizon forever. And because the universe is expanding, this horizon is actually shrinking in a sense. Galaxies that we can see now will eventually be carried away from us by the expansion of space, moving so far away that their light will never reach us again. In the far future, observers in the Milky Way will look out and see almost nothing. A few nearby galaxies in our local group, and then darkness. The rest of the universe will have receded beyond the horizon. But I'm getting off track. Let's bring this back to the shape of the universe and what it means for expansion. If the universe is flat and infinite, as current evidence suggests, then it's not expanding into anything because there is no outside. It's just infinite space becoming less dense. The distances between galaxies are increasing, but the total extent of space was always infinite. But here's where things get philosophically interesting. Even if the universe is finite, even if it's a closed universe curving back on itself, asking what it's expanding into might still be the wrong question. Remember, even a closed universe doesn't have a boundary. There's no edge. If you're inside the universe, whether it's finite or infinite, there's no place you can go to find the outside. The universe is all there is. Yes, mathematically, we can describe a closed universe as a three-dimensional surface embedded in four-dimensional space. And yes, in that mathematical description, the universe is expanding into that fourth dimension. But that fourth dimension isn't part of physical reality as we experience it. It's a mathematical construct we use to describe the geometry. It's like how we can describe a curved line on a piece of paper using equations that reference a coordinate system. The coordinate system isn't physically real, it's just a tool we use to describe the curve. Similarly, the higher dimensional space we might use to describe a closed universe isn't physically real. It's just a mathematical convenience. So even in a closed universe, from the perspective of anyone living inside it, there's no outside. The universe is still all there is. This is one of those situations where our language and our intuitions fail us. We use words like expanding and growing and increasing in size, and all of those words carry connotations from our everyday experience. When something expands, it pushes into the space around it. But the universe isn't like that. The universe isn't expanding into space. The universe is space. And space itself is changing, evolving, its geometry shifting over time. The relationships between distant objects are changing. That's what expansion means in this context. Not motion through space, but the evolution of space itself. There's a useful analogy that cosmologists sometimes use, though like all analogies, it has its limitations. Imagine a loaf of raisin bread dough rising in an oven. As the dough expands, the raisins embedded in it move farther apart. But the raisins aren't moving through the dough. They're being carried along by the expansion of the dough itself. From the perspective of any individual raisin, all the other raisins appear to be moving away. And the farther away a raisin is, the faster it appears to be receding. This is exactly what Hubble observed with galaxies. Now, the analogy breaks down because the bread dough is expanding into the air inside the oven. But if we imagine that the dough is all there is, that there is no oven, no air, no outside, just the dough itself, then we start to get closer to the reality of the universe's expansion. The dough isn't expanding into anything. It's just expanding. The volume of dough is increasing, or if the dough is infinite, the density of raisins is decreasing. But there's no external space that the dough is pushing into. Another way to think about this, and this is more mathematically precise, is in terms of the metric of space. The metric is a mathematical object that describes distances and geometry. In general relativity, the metric can change over time. When we say space is expanding, we mean the metric is changing in such a way that the distance between distant objects increases. This is called metric expansion. And, crucially, objects don't have to move through space for this to happen. The space itself, the geometry itself, is evolving. Galaxies are mostly just sitting still in their local patch of space, but the space between them is growing. There's one more aspect of this we need to address, and it has to do with something called the cosmological horizon, or the Hubble sphere. Because space is expanding, there's a distance beyond which objects are receding from us faster than the speed of light. Wait, you might say. I thought nothing could move faster than light? That's one of the fundamental principles of relativity. And you'd be right. Nothing can move through space faster than light. But space itself can expand as fast as it wants. There's no speed limit on the expansion of space. So, if a galaxy is far enough away, the expansion of space between us and that galaxy can cause it to recede from us faster than light. This doesn't violate relativity, because the galaxy isn't actually moving through space at faster than light speeds. It's just that so much space is being created between us and the galaxy that the distance is increasing faster than light could cross it. The boundary where this happens is called the Hubble sphere. Galaxies beyond the Hubble sphere are receding faster than light. Light from those galaxies is still traveling toward us, but it's fighting against the expansion of space, and it's losing. In fact, in the current model of the universe's expansion, which includes something called dark energy, the Hubble sphere will eventually encompass all but our local group of galaxies. Everything else will be carried beyond the horizon, receding faster than light, forever out of reach. But again, even this doesn't mean the universe is expanding into something. These galaxies aren't moving into some external void. They're just getting farther away as space expands. So, where does all of this leave us? If the universe is flat and infinite, it's not expanding into anything. It's just infinite space becoming less dense. If the universe is closed and finite, It might be mathematically described as expanding into a higher dimension, but that higher dimension isn't physically accessible or meaningful to us. Either way, there's no outside to the universe. No edge, no boundary, no void that we're expanding into. The universe is all there is, and I know this is frustrating. It feels like we're dodging the question. But we're not. This is the answer. The question itself is based on a flawed assumption, an assumption that comes from our everyday experience of objects in space. We assume the universe must be like those objects, expanding into something larger. But it's not. The universe is the totality of space itself, and space doesn't need something to expand into. It just expands. Let's talk about infinity, not as an abstract mathematical concept, but as a physical reality. Because if the universe is truly infinite, as current evidence suggests, then we need to confront what that actually means. And, more importantly, we need to address what might be the most confusing aspect of this entire discussion. How can an infinite universe expand? Think about it. Infinity means without limit, without end, without boundary. It's the biggest thing there is. You can't add to infinity. You can't make it bigger. Infinity plus 1 is still infinity. Infinity times 2 is still infinity. So if the universe is already infinite, how can it be getting bigger? This seems like a logical contradiction. And this is where a lot of people get stuck. They hear that the universe is infinite and expanding, and their brain just refuses to accept that both things can be true simultaneously. But here's the key insight. When we say the universe is expanding, we don't mean its size is increasing. We mean its density is decreasing. Let me say that again because it's crucial. In an infinite universe, expansion doesn't mean the universe is getting bigger. It means the stuff in the universe is getting more spread out. The distance between any two galaxies is increasing, but the total volume was always infinite, and still is infinite. Think of it this way. Imagine you have an infinite number line stretching forever in both directions. Now, imagine there's a marker at every integer, 1 at 0, 1 at 1, 1 at 2, and so on, forever in both directions. Now, let's say we apply a transformation to this number line. Every marker moves away from 0. The marker at 1 moves to 2. The marker at 2 moves to 4. The marker at 3 moves to 6. Every position gets multiplied by 2. The spacing between markers has doubled. They're twice as far apart as they were before. But the number line itself? Still infinite. We haven't made the number line bigger. It was already infinitely long. We've just changed the density of markers on it. This is exactly what's happening with the expansion of the universe. The universe itself isn't growing because it was already infinite. But the distance between galaxies is increasing. The density of matter in space is decreasing. Space is stretching, but the total amount of space was always infinite. Now, you might object. You might say, but wait, if we're adding more space between galaxies, where is that new space coming from? Isn't that increasing the total amount of space? And this brings us back to a point we touched on earlier. Space isn't a substance. It's not made of anything. It's a geometric relationship between events and objects. When we say more space is being created between two galaxies, we're not saying some kind of space stuff is being manufactured and inserted between them. We're saying the geometric relationship is changing. The distance, as measured by how long it takes light to travel from one galaxy to the other, is increasing. But distance isn't a thing. It's a property, a relationship. You can't have a pile of distance sitting in a warehouse somewhere. Distance is a description of how things relate to each other spatially. And in an expanding universe, those relationships are changing. The metric, the mathematical description of distances and geometry, is evolving over time. Another way to think about this is through the concept of scale factor. Cosmologists use something called the scale factor to describe how the universe has expanded over time. If we set the scale factor today to 1, then in the past the scale factor was smaller, and in the future it will be larger. When the scale factor doubles, it means that the distance between any two distant objects has doubled. But the universe itself, if it's infinite, is still infinite. The scale factor can increase from 1 to 2 to 1,000,000 to 1,000,000,000, and infinity times any finite number is still infinity. The total extent of the universe doesn't change because infinity can't change. What changes is the density, the spacing, the geometric relationships. So when we rewind the clock, when we run the expansion backward toward the Big Bang, what happens? If the universe is infinite now, it must have been infinite then too. But as we go back in time, the scale factor gets smaller and smaller. The distances between things shrink. The density of matter and energy increases. The temperature rises. And as we approach the moment of the Big Bang, the scale factor approaches 0. Not reaches 0, but approaches it. The density approaches infinity. The temperature approaches infinity. Every point in space was arbitrarily close to every other point. But there were still infinitely many points. This is what cosmologists mean when they talk about the Big Bang singularity. It's not a point in space where everything was located. It's a moment in time when the density and temperature of the universe were infinite everywhere. The singularity isn't a place, it's a when. It's the t equals 0 moment on the cosmic timeline. Now, here's where things get philosophically strange. If the universe was infinite at the Big Bang, and it's infinite now, in what sense did the Big Bang actually begin anything? The answer is that the Big Bang was the beginning of time, but not necessarily the beginning of space. Space may have always existed, stretching infinitely in all directions. But at t equals 0, or rather at the earliest moment we can meaningfully talk about, that infinite space was in a state of infinite density and temperature. Time itself may have begun at that moment. This raises all sorts of thorny questions about causality and what it even means for time to begin. If there was no before the Big Bang, then what caused the Big Bang? These are questions that push at the boundaries of physics and tip over into philosophy and metaphysics. Some cosmologists believe the singularity isn't real, that it's an artifact of our theories breaking down at extreme conditions. Quantum gravity effects, which we don't yet understand, might have prevented the density from actually becoming infinite. There might have been a brief period before the Big Bang, a quantum foam or a previous contracting phase that bounced into our current expansion. But these are all speculative ideas. What we know for sure is that the universe was once much, much denser and hotter than it is today, and it's been expanding and cooling ever since. Whether that expansion started from a true singularity or from some earlier quantum state, we don't yet know. But let's set aside the Big Bang for a moment and focus on another aspect of infinity and expansion: the observable universe. We talked earlier about how the observable universe is finite, a sphere about 93 billion light-years across, centered on us. This is the region from which light has had time to reach us since the Big Bang. But if the entire universe is infinite, then our observable universe is just a tiny bubble within that infinity. And here's something remarkable. Every point in the universe has its own observable universe, a sphere of the same size centered on that point. If you traveled to a galaxy 50 billion light-years away, you'd have a different observable universe. You'd see different galaxies, different structures. Some of the galaxies we can see would be beyond your horizon, and some of the galaxies you could see would be beyond ours. In an infinite universe, there are infinitely many such observable universe-sized regions, all overlapping, all slightly different. And because the universe is expanding, the relationship between these regions is changing. Light that's traveling between distant regions is being stretched by the expansion. The wavelength of the light increases, shifting it toward the red end of the spectrum. This is the red shift that Hubble discovered. The farther away a galaxy is, the more the light from it has been stretched by the expansion, and the more red-shifted it appears. But there's a limit to how far we can see. Not because there's nothing beyond that limit, but because light from beyond a certain distance hasn't had time to reach us yet. As time goes on, we'll be able to see a bit farther. Light from previously invisible regions will finally arrive. Our observable universe is growing. But here's the twist. Because the expansion of the universe is accelerating, there are galaxies we can see now that we won't be able to see in the far future. They're being carried away from us so fast that eventually their light will be red-shifted into oblivion. The photons will be stretched to such long wavelengths that they'll be undetectable. In a sense, our cosmic horizon is both expanding and contracting. We can see farther into space, but the number of galaxies within our reach is decreasing. This accelerating expansion is driven by something called dark energy, a mysterious component of the universe that acts like a repulsive form of gravity. We don't know what dark energy is. We just know it's there because we can measure its effects. And those effects are dramatic. In the far future, billions of years from now, the universe will be a much lonelier place. Almost all galaxies will have been carried beyond our cosmic horizon. Observers in the Milky Way will look out and see only the handful of galaxies in our local group, gravitationally bound to us. Everything else will be gone, invisible, unreachable. The night sky will be dark. And if intelligent beings exist at that time, if they try to do cosmology, they won't be able to discover the expansion of the universe because there won't be any distant galaxies to measure. They'll think they live in a static universe consisting of just a few galaxies surrounded by infinite empty space. They'll be completely wrong, but they'll have no way to know it. All the evidence will have literally moved beyond their reach. This is a sobering thought. It suggests that our own understanding of the universe might be limited by what happens to be observable from our particular location in space and time. There could be features of the universe, large-scale structures or phenomena, that existed in the past or will exist in the future, but that we'll never be able to detect because the light from them will never reach us. We are seeing the universe through a very specific window, and that window is shaped by the expansion, by the speed of light, and by the age of the universe. So let's bring this back to the question of what the universe is expanding into. We've established that if the universe is infinite, it's not expanding into anything, it's just becoming less dense. But we've also established that the observable universe is finite and growing. So, in what sense is the observable universe expanding? Is it expanding into the previously unobservable parts of the infinite universe? In a sense, yes. As time goes on, light from more distant regions reaches us, and our observable universe encompasses more of the infinite whole. But this isn't the universe expanding into something external. It's just our view of the universe expanding. We're seeing more of what was always there. It's like standing on a mountaintop as the fog lifts. As the fog clears, you can see more of the landscape. The landscape was always there. You just couldn't see it before. Your visible area is expanding, but the landscape itself isn't expanding into anything. Similarly, the observable universe is expanding in the sense that we can see more and more of the infinite universe as time passes. But the universe itself isn't expanding into some external space. Now, let's tackle another aspect of this that often confuses people: energy conservation. If space is expanding, if more space is being created between galaxies, doesn't that violate the law of conservation of energy? After all, empty space isn't actually empty. It has energy associated with it. Quantum field theory tells us that even the vacuum of space is seething with virtual particles popping in and out of existence. And dark energy, whatever it is a form of energy that permeates all of space. So, if space is expanding and dark energy fills that space, aren't we creating energy out of nothing? The answer is complicated. In general relativity, energy conservation is a tricky concept. In a static spacetime, energy is conserved. The total amount of energy doesn't change over time. But in an expanding spacetime, the definition of energy becomes ambiguous. There isn't a single, well-defined notion of total energy for the universe as a whole. The energy of matter and radiation does change over time due to the expansion. Photons get redshifted, losing energy. The cosmic microwave background radiation, which was once hot enough to ionize atoms, is now just a few degrees above absolute zero. Where did that energy go? In a sense, it was lost to the expansion. The wavelength of each photon stretched, and in the process, the energy decreased. This doesn't violate energy conservation in the usual sense because energy conservation in general relativity is a local law, not a global one. Locally, in small regions of space, energy is conserved. But globally, across the entire expanding universe, energy can change. As for dark energy, it's even stranger. As space expands, the volume of space increases. And if dark energy has a constant density, meaning a constant amount of energy per unit volume, then the total dark energy in any given volume of space increases as that volume expands. New dark energy is being created as space expands. This sounds like a violation of energy conservation, and in a sense it is. But again, general relativity doesn't require global energy conservation in an expanding universe. The rules are different. And this ties into something deep about the nature of energy and space-time. Energy isn't a substance. It's a property of fields and particles, and it's defined relative to a particular space-time geometry. When that geometry is changing, as it is in an expanding universe, the notion of energy becomes context-dependent. Some physicists argue that if you account for the gravitational field properly, the total energy of the universe, including gravity, might actually be zero. The positive energy of matter and radiation is balanced by the negative energy of the gravitational field. In this view, the universe is a free lunch. Everything cancels out, and no energy conservation is violated because there was never any net energy to begin with. But this is a contentious idea, and not all physicists agree on it. The point is, the expansion of the universe and the behavior of energy in that expansion are consistent with general relativity, even if they seem to violate our intuitive notions of energy conservation. So, what have we learned? An infinite universe can expand in the sense that its density decreases, even though its total size remains infinite. The Big Bang wasn't an explosion at a point in space, but a moment in time when the entire infinite universe was in a state of infinite density. The observable universe is a finite bubble within the infinite whole, and that bubble is growing as light from more distant regions reaches us. But none of this involves the universe expanding into anything external. There's no outside, no void, no pre-existing space that the universe is filling. The universe is all of space, and space itself is evolving, changing, expanding. And if this seems counterintuitive, if it feels like we're playing word games or avoiding the question, remember that the universe doesn't care about our intuitions. It doesn't owe us an explanation that makes sense in terms of our everyday experience. Our everyday experience is limited to a tiny corner of reality, a thin slice of space-time on the surface of a small planet orbiting an ordinary star. The universe as a whole operates according to different rules we've only recently begun to understand. And those rules, strange as they may seem, are telling us that the universe is not an object in space. It is space. And space, infinite and ever-changing, is all there is. We need to talk about the Big Bang. Because even after everything we've discussed, even after we've established that the universe might be infinite and that it's not expanding into anything, there's still this nagging question. If the universe is infinite now, and it was infinite at the Big Bang, how do we reconcile that with the popular image most people have of the Big Bang as some kind of explosion from a single point? This is where a lot of the confusion comes from. The way the Big Bang is typically portrayed in documentaries and textbooks, you see this dramatic animation. A tiny point of light in the darkness, and then boom, it explodes outward, expanding in all directions, creating space and time and matter and energy. It looks like an explosion happening in pre-existing space, like a firework going off in the night sky. But that's not what the Big Bang was. That's not even close to what the Big Bang was. The Big Bang didn't happen at a location. It didn't happen in some pre-existing void. It happened everywhere, simultaneously, throughout all of space. Let me try to explain this more carefully, because it's one of the most important and most misunderstood concepts in all of cosmology. When we rewind the expansion of the universe, when we go backward in time, we're not watching some ball of matter contract toward a single point. We're watching the entire universe, infinite or finite, become denser and hotter. Every cubic centimeter of space contained more matter, more energy, higher temperature, higher pressure. Go back far enough, and every cubic centimeter of space contained a star's worth of matter. Go back farther, and every cubic centimeter contained a galaxy's worth of matter. Keep going, and eventually you reach a time when the entire observable universe, that 93 billion light-year-wide sphere we talked about earlier, was compressed into a region smaller than an atom. But here's the key. That compressed region was still just our observable universe. The rest of the infinite universe, all those other observable universe-sized regions, they were also compressed. Every point in space was part of this hot, dense state. There was no center. There was no edge. There was no single point where it all was. If you could somehow exist at that moment and look around, you wouldn't see everything compressed into a point off in the distance. You'd see a hot, dense, uniform plasma extending in all directions, forever. Of course, you couldn't actually see anything because photons couldn't travel freely through that plasma, but you get the idea. So, when cosmologists talk about the Big Bang singularity, they're not talking about a point in space. They're talking about a moment in time. A moment when the density and temperature of the universe at every point in space approached infinity. The singularity isn't a place, it's a when. Now, I said approached infinity rather than reached infinity because we don't actually know what happened at the exact moment of t equals 0. Our theories break down. General relativity, which describes gravity and the large-scale structure of space-time, predicts that there should be a singularity, a point of infinite density and infinite curvature. But we know general relativity can't be the whole story because it doesn't account for quantum mechanics. And at the incredibly small scales and high energies present near the Big Bang, quantum effects should be dominant. We need a theory of quantum gravity to describe what really happened. And we don't have one yet. There are candidates, like string theory and loop quantum gravity, but none of them are complete or experimentally verified. So when we talk about the Big Bang, we're really talking about the earliest moment we can describe with confidence using known physics. That's about a tiny fraction of a second after t equals 0, a time called the Planck time, which is about 10 to the minus 43 seconds. Before that, we're in uncharted territory. But let's set aside the unknown physics of the first instant and focus on what we do know. At some very early time, the universe was in a hot, dense, uniform state. It was so hot that atoms couldn't exist. Even atomic nuclei couldn't exist. It was just a soup of fundamental particles, quarks and electrons and photons and neutrinos, all colliding with each other at incredible energies. And this state existed everywhere, throughout all of space. Then, as the universe expanded, as the scale factor increased, the density dropped and the temperature dropped. The particles slowed down. Eventually, it became cool enough for quarks to bind together into protons and neutrons. Then, a few minutes after the Big Bang, it became cool enough for protons and neutrons to fuse into the lightest atomic nuclei, hydrogen and helium, and a tiny bit of lithium. This process, called Big Bang nucleosynthesis, lasted for about 17 minutes. After that, the universe was too cool and too diffuse for fusion to continue. For the next several 100,000 years, the universe was filled with this hot plasma of nuclei and electrons and photons. The photons were constantly scattering off the electrons, bouncing around in all directions. The universe was opaque. Light couldn't travel freely. But as the universe continued to expand and cool, eventually it reached a temperature where electrons could bind to nuclei to form neutral atoms. This process, called recombination, happened about 300 to 80,000 years after the Big Bang. And once atoms formed, the photons were no longer scattering off free electrons. They could travel freely through space. The universe became transparent. Those photons have been traveling through space ever since, redshifted by the expansion from visible light into microwaves. That's the cosmic microwave background we talked about earlier. It's a snapshot of the universe at the moment it became transparent, a baby picture of the cosmos. And when we look at that baby picture, we see something remarkable. The universe was incredibly uniform. The temperature variations across the sky are only about 1 part in 100,000. Everywhere we look, the early universe had almost exactly the same density and temperature. This uniformity is actually a bit of a puzzle. How did regions of the universe that were so far apart that light couldn't have traveled between them end up at the same temperature? If they were never in contact, never able to exchange energy or information, how did they coordinate to be so similar? This is called the horizon problem, and it was one of the major mysteries in cosmology for decades. The solution, proposed in the 1980s by physicist Alan Guth and others, is called inflation. The idea is that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space expanded faster than the speed of light, much faster, doubling in size over and over again in the blink of an eye. This sounds like it violates relativity, but remember, nothing can move through space faster than light. Space itself, however, can expand as fast as it wants. During inflation, the universe expanded by a factor of at least 10 to the 26 in a time period of about 10 to the minus 32 seconds. That's a trillion times bigger in less than a trillionth of a trillionth of a trillionth of a second. It's hard to even comprehend expansion at that rate. Before inflation, the entire observable universe was much, much smaller. All the regions we can see today, spread across 93 billion light-years, were once packed into a space smaller than an atom. And at that tiny size, they were in contact. They could exchange energy and reach the same temperature. Then inflation blew them apart, separating them by vast distances faster than light could travel between them. But they retained the memory of their original uniform state. That's why the cosmic microwave background looks so uniform. Inflation solves the horizon problem. It also explains other features of the universe, like why it's so flat. But here's the thing. Inflation doesn't change the fundamental nature of what we've been discussing. If the universe is infinite after inflation, it was infinite before inflation too. Inflation just made an already uniform region exponentially larger. And if the universe is finite, inflation made it much, much bigger, but still finite. The question of what the universe is expanding into isn't answered by inflation. It just pushes the question back to an earlier time. Now, here's where things get really interesting. Some versions of inflation, particularly a model called eternal inflation, suggest that inflation never completely stops. In most of the universe, inflation is still happening, space expanding exponentially. But in some regions, quantum fluctuations cause inflation to end, and those regions become what we call universes. Our universe is one such region where inflation ended and the hot Big Bang phase began. But beyond our universe, inflation continues, spawning more and more bubble universes, each with potentially different physical properties. This is the multiverse hypothesis. And if it's true, then our universe, the totality of everything we can observe or ever could observe, is just one bubble in an eternally inflating space. And here's where we finally might have an answer to our original question. If the multiverse is real, if our universe is a bubble within an eternally inflating background space, then maybe, just maybe, our universe is expanding into that larger space. The bubble is growing. The boundary between our universe and the inflating region outside is moving outward. But, and this is crucial, we can never access that outside region. We can never observe it, or travel to it, or interact with it in any way. The physics inside our bubble is different from the physics outside. The inflating region doesn't have matter or galaxies or stars. It's just expanding space, stretching faster and faster, forever. So even in this scenario, even if we grant that there's something outside our universe, it's not an outside that's meaningful to us. It's not a place we could go or a space we could explore. It's beyond the boundary of our reality in a fundamental way. And we should emphasize, the multiverse is speculative. It's a prediction of some versions of inflation, but we don't have any direct evidence for it. We might never have evidence for it because, by definition, other universes are beyond our observable horizon. Some physicists embrace the multiverse as the natural consequence of inflation. Others reject it as untestable and therefore unscientific. It's an ongoing debate. But whether the multiverse exists or not, the basic point remains. Our universe, as we experience it, is not expanding into any external space that we can access or observe. If there is an outside, it's forever beyond our reach. Let's shift gears and talk about another aspect of the early universe that's often misunderstood: the Big Bang and time itself. We said earlier that the Big Bang might have been the beginning of time. But what does that even mean? How can time begin? Doesn't the concept of beginning presuppose that there was a before and an after, which requires time to already exist? This is one of those questions that seems paradoxical until you really think about what time is. In general relativity, time is not a separate entity from space. It's part of space-time, a four-dimensional fabric. And space-time can have a boundary. It can have an edge in the time direction. Imagine a space-time diagram where one axis is space and the other is time. If you trace the history of the universe backward, you're moving down the time axis toward smaller and smaller values of a to t. And if space-time has a boundary, you reach a point where there is no farther back. The time axis ends. That's the Big Bang. Not a moment in time, but the edge of time itself. Before the Big Bang, there is no before. It's not that something existed in some timeless void. It's that the concept of before doesn't apply. Time itself begins at the Big Bang. The question, what happened before the Big Bang, is like asking what's north of the North Pole. The question is grammatically valid, but conceptually meaningless. Once you're at the North Pole, there is no north. Once you're at the Big Bang, there is no before. Now, some cosmological models do propose that time extends before the Big Bang. Some versions of quantum cosmology suggest the universe could have emerged from a timeless quantum state. A state that exists in a sense, but not in time. Other models propose a cyclic universe that expands and contracts eternally, with each Big Bang being the bounce from a previous contraction. In these models, time might be eternal with no beginning or end. But in the standard Big Bang model, time begins at the Big Bang. And this has profound implications. It means the universe doesn't need a cause in the traditional sense. Causes happen in time. One event causes another event that comes after it. But if time itself begins at the Big Bang, there's no time for a cause to exist in. The Big Bang is the first event. There's nothing before it, not even time. This doesn't sit well with a lot of people. Our intuition tells us that everything must have a cause. But that intuition is based on our experience within time. When we're talking about the origin of time itself, those intuitions don't apply. It's also worth noting that even if the Big Bang was the beginning of time, that doesn't necessarily mean the universe was created from nothing. The quantum vacuum, the state we think of as empty space, is actually full of energy and virtual particles. Some physicists have proposed that the universe could have emerged from a quantum fluctuation of the vacuum, a spontaneous event allowed by the uncertainty principle. In this view, the universe is a quantum event, not fundamentally different from a particle popping into existence in a particle accelerator. It's bizarre, it's counterintuitive, but it's consistent with quantum mechanics. And if the total energy of the universe is zero, with the positive energy of matter balanced by the negative energy of gravity, then the universe doesn't violate conservation of energy, even if it came from nothing. Of course, all of this is speculative. We don't know what happened at the Big Bang or what, if anything, came before. These are open questions at the frontier of physics. But the point is, the Big Bang forces us to rethink our most basic assumptions about time, causality, and existence. It challenges us to let go of our intuitive notions and embrace the strange reality that the universe might be fundamentally different from anything we experience in our everyday lives. So let's bring this full circle. We started with the question, what is the universe expanding into? And we've seen that the answer depends on understanding what space is, what expansion means, and what the Big Bang was. Space is not a container. It's a set of geometric relationships. Expansion doesn't mean moving into something. It means those geometric relationships are changing. And the Big Bang wasn't an explosion at a point. It was a moment when all of space was in a hot, dense state. If the universe is infinite, it's not expanding into anything because it was always infinite. The expansion just means it's becoming less dense. If the universe is finite, it might be mathematically described as embedded in a higher dimensional space, but that higher dimension is not physically real or accessible to us. Either way, there's no outside, no edge, no void the universe is filling. The universe is all there is. And if that answer seems unsatisfying, if it feels like a cop-out, consider this. The question itself might be the problem. We're asking a question that assumes the universe is an object, a thing, when really the universe is the totality of all things. We're trying to apply concepts from within space to space itself, and that leads to confusion. The universe doesn't expand into space. The universe is space, and space is all there is. We've spent a lot of time exploring the physics, the mathematics, the geometry of the universe and its expansion. We've learned that space isn't a container, that infinity can expand by becoming less dense, that the Big Bang wasn't an explosion at a point, but a moment when all of space was hot and dense. We've established, as firmly as our current understanding allows, that the universe is not expanding into anything because there is no outside. But I want to take a step back now and ask a different kind of question. Not what is the answer, but why do we struggle so much with the answer? Why does our brain rebel against this idea? Why does it feel so deeply unsatisfying to be told that the question itself is flawed? The answer, I think, tells us something profound about the nature of human cognition and our place in the cosmos. We are pattern recognition machines. Our brains evolved over millions of years to make sense of the world around us, to identify threats and opportunities, to navigate through three-dimensional space, to predict the behavior of objects and other animals. Every aspect of our mental architecture is tuned to the environment in which we evolved. A world of medium-sized objects moving at medium speeds under the influence of gravity. We evolved to understand rocks and trees and rivers. We evolved to throw spears and climb mountains and recognize faces. We did not evolve to understand the large-scale structure of the universe or the behavior of space itself. And so, when we try to think about cosmology, when we try to wrap our heads around concepts like infinite space or the expansion of space or the beginning of time, we're using cognitive tools that were never designed for this purpose. It's like trying to use a hammer to tighten a screw. The tool works, sort of, but it's not the right tool for the job. Our intuition, that deep gut feeling about how the world works is based on everyday experience. And everyday experience tells us that objects exist in space, that space is like a container, that when something expands, it must be expanding into something else. These intuitions are correct for the situations in which they evolved. A balloon does expand into the air around it. A city does expand into the surrounding countryside. Every expanding thing we've ever encountered in our lives has been expanding into something. So, of course, our brain generalizes this pattern. Of course, we assume the universe must work the same way. But the universe doesn't work that way. And this is where we hit a wall. We can understand the mathematics. We can follow the logic. We can see that the equations of general relativity describe a space-time that can be curved and can expand without needing an outside. But emotionally, intuitively, it still feels wrong. There's a gap between intellectual understanding and intuitive acceptance. And that gap, I would argue, is unavoidable. Some truths about reality are simply beyond the reach of human intuition. Our brains are finite. They're the product of a particular evolutionary history. They're optimized for survival in a specific environment, not for understanding the fundamental nature of reality. And yet, remarkably, we've managed to develop tools that extend beyond our intuitions. Mathematics, logic, the scientific method. These allow us to explore realms that our brains were never equipped to handle. We can't visualize four-dimensional space, but we can describe it with equations. We can't intuitively grasp quantum mechanics, but we can test its predictions with exquisite precision. We can't feel the expansion of space, but we can measure it with telescopes. This is one of humanity's greatest achievements. We've transcended our cognitive limitations. We've built a ladder that reaches beyond our immediate perception and into the deep structure of the cosmos. But we're still climbing that ladder. We're still apes, in a very real sense, trying to understand things that no ape brain was designed to understand. And that's okay. It's actually beautiful. There's something poetic about the fact that we're smart enough to ask questions about the nature of the universe, but not quite smart enough to intuitively grasp the answers. We exist in this strange middle ground between ignorance and omniscience. We can peek behind the curtain, but we can't fully process what we see. So, when you feel frustrated by the answer to the question, what is the universe expanding into? When you feel that sense of dissatisfaction, that nagging feeling that we're dodging the question or playing word games, recognize that feeling for what it is. It's your brain doing what it was designed to do. It's trying to fit new information into old patterns. It's trying to make sense of the universe using tools that were built for a much smaller, much simpler world. And those tools are failing. Not because you're not smart enough, but because the tools themselves are inadequate. The universe is under no obligation to make sense to you. It's under no obligation to conform to your intuitions or to provide answers that feel satisfying. The universe simply is. And our job, as curious beings, is to observe it, measure it, and describe it as accurately as we can, even when that description challenges everything we think we know. Let's talk about some analogies that people use to try to make the expansion of the universe more intuitive. We've mentioned a few already, like the rubber sheet with coins on it or the raisin bread dough. These analogies are useful up to a point, but they all break down eventually because they all depict the universe as an object embedded in a larger space. The rubber sheet exists in three-dimensional space. The bread dough expands into the oven. No matter what analogy we use, if we're trying to visualize it, we're necessarily placing it within some larger context. And that's the problem. There is no larger context for the universe. One analogy that gets a bit closer is the surface of a balloon. Imagine drawing dots on a balloon with a marker and then inflating the balloon. As the balloon expands, the dots move apart. And if you're a two-dimensional creature living on the surface of that balloon, you'd see all the other dots moving away from you. The farther away a dot is, the faster it appears to be receding. This is exactly what we observe with galaxies. Now, the key insight here is that the two-dimensional surface creatures don't experience the three-dimensional space that the balloon is embedded in. They can't point to it. They can't access it. Their entire universe is the two-dimensional surface. And when the balloon expands, they don't perceive it as expanding into anything. They just see the distances between dots increasing. This is a decent analogy for our situation. We're three-dimensional creatures living in a three-dimensional space that might be curved through a higher dimension. But we can't access that higher dimension. We can't point to it. Our entire universe is the three-dimensional space. And when it expands, we see distances increasing, but there's no outside for us to perceive. The analogy breaks down, of course, because we can visualize the balloon from outside. We can see it as an object in space. But that's our limitation, not a feature of reality. The point is, even our best analogies are imperfect. They're crutches to help us limp toward understanding, but eventually we have to let go of the crutches and engage with the mathematics directly. And the mathematics tells us unambiguously that the universe doesn't need an outside. There's another way to think about this that might help. Consider the question, where's the center of the universe? If you ask most people, they'll probably say something like, well, it's wherever the Big Bang happened. That's where everything expanded from, so that must be the center. But we've already established that the Big Bang didn't happen at a location. It happened everywhere. So there is no center. Every point in the universe is, in a sense, the center. If you're standing on Earth, you see galaxies receding in all directions. If you traveled to a galaxy 1 billion light-years away, you'd see the same thing. Galaxies receding in all directions from your new location. There's no special point, no center from which everything is expanding. This is called the cosmological principle. The universe looks the same from every vantage point. It's homogeneous and isotropic on large scales. Now, if there's no center, then the idea of the universe expanding into something external becomes even more problematic. Expansion into what? From where? If there's no center and no edge, the universe isn't moving into anything. It's just changing internally. Here's yet another way to think about it. Imagine you're playing a video game. The game world has a certain size, a certain number of pixels. Now imagine the game developers release an update that increases the resolution. The world looks the same, but now there are more pixels. The distance between two characters in the game, measured in pixels, has increased. But the game world didn't expand into anything external. There's no space outside the game world. The game world is all there is within the context of the game. The expansion happened internally, as a change in the structure of the world itself. This is similar to what's happening with the universe. The metric of space, the mathematical description of distances, is changing. The resolution, in a sense, is increasing. But there's no external space that this is happening within. It's an internal change to the structure of space itself. Of course, the universe isn't a video game. It's not a simulation running on some cosmic computer, at least as far as we know. But the analogy helps illustrate how something can expand or change without needing an outside. Okay, let's address the elephant in the room, the multiverse. We touched on this earlier, but it deserves a deeper look because it's one of the few scenarios where we might legitimately say the universe is expanding into something. The multiverse hypothesis comes in several flavors, but the most relevant one for our discussion is the one that emerges from eternal inflation. In this model, inflation, that exponential expansion in the first fraction of a second after the Big Bang, doesn't end everywhere at once. It ends in some regions due to quantum fluctuations, and those regions become universes like ours. But in other regions, inflation continues, and those regions spawn more bubble universes, which spawn more ad infinitum. The result is an eternally inflating multiverse, a vast, possibly infinite expanse of space undergoing eternal exponential expansion, dotted with bubble universes like ours where inflation has ended and normal physics has taken over. In this picture, our universe is one bubble among countless others, and our bubble is expanding. The boundary between our universe and the inflating region outside is moving outward. So, in this sense, our universe is expanding into something. It's expanding into the eternally inflating background space. But here's the catch. That background space is not accessible to us. The inflating region is expanding faster than light, much faster. Any signal from outside our bubble can never catch up to us. We're causally disconnected from the rest of the multiverse. We can never observe it, travel to it, or interact with it. It's beyond our cosmic horizon in a fundamental and permanent way. Moreover, the physics in the inflating region is different. It doesn't have matter or stars or galaxies. It's just space expanding exponentially. In some sense, it's not even clear if we should call it space. It's more like a quantum field in a highly excited state. So, even if we grant that the multiverse is real and that our universe is expanding into this larger structure, it doesn't really solve the problem. We're still left with the question, what is the multiverse expanding into? And if the multiverse is infinite, which some versions suggest, then we're back to square one. An infinite multiverse doesn't need to expand into anything. It's just becoming less dense in some regions and more dense in others. And we should emphasize again, the multiverse is speculative. It's not proven. It might not even be testable. Some physicists argue it's not science at all because science requires the ability to make predictions and test them. If other universes are forever beyond our reach, how can we ever know if they exist? Others argue that the multiverse is a natural prediction of inflation, and inflation is supported by evidence, so we should take the multiverse seriously even if we can't directly observe it. It's a fascinating debate, but for our purposes the point is that even the multiverse doesn't really answer the question of what the universe is expanding into. It just pushes the question to a larger scale. Let's take a moment to appreciate just how far we've come in our understanding. A little over a century ago, we didn't even know that other galaxies existed. We thought the Milky Way was the entire universe. Then, in the 1920s, Hubble showed us that those fuzzy nebulae in the night sky were actually distant galaxies, and that those galaxies were all moving away from us. The universe was expanding. In the decades since, we've measured that expansion with increasing precision. We've looked back to the early universe and seen the cosmic microwave background, the afterglow of the Big Bang. We've mapped the large-scale structure of the universe, the cosmic web of galaxies and voids. We've discovered dark matter and dark energy, mysterious components that make up most of the universe but that we barely understand. We've developed a standard model of cosmology, the lambda CDM model, that describes the evolution of the universe from the first fraction of a second to the present day with remarkable accuracy. We've tested this model against observations and found it holds up again and again. And all of this has led us to a picture of the universe that's both awe-inspiring and deeply strange. A universe that might be infinite, that's been expanding for nearly 14 billion years, that had a beginning but no cause, that's filled with invisible matter and permeated by a repulsive energy we don't understand. A universe that's not expanding into anything because it is everything. It's a picture that challenges our intuitions at every turn. But it's also a picture that is supported by a mountain of evidence. It's the best answer we have to the question of what the universe is and how it works. And if that answer is unsatisfying, if it leaves you with more questions than answers, good. That's the mark of a curious mind. Science isn't about providing comfortable, intuitive answers. It's about following the evidence wherever it leads, even when it leads to places that feel alien and incomprehensible. The question, what is the universe expanding into, is a perfect example of how our everyday intuitions can lead us astray. It's a question that feels like it should have a simple answer, but the truth is, the question is based on a flawed assumption. The assumption that the universe is an object in space, rather than space itself. Once we let go of that assumption, once we really internalize what it means for the universe to be all of space, the question dissolves. It's not that we can't answer it, it's that there's nothing to answer. The universe isn't expanding into anything. It's just expanding. Distances are increasing. Space is becoming less dense. The geometry is evolving. But there's no outside, no boundary, no edge advancing into a void. And if you find this frustrating, if you feel like we've spent all this time just to arrive at what seems like a non-answer, I understand. I really do. It's frustrating to me too, in a way. Our brains want closure. We want satisfying answers. We want the universe to make sense in terms we can grasp. But the universe doesn't owe us that. The universe is what it is, independent of what we want or expect or find intuitive. And part of the journey of science, part of the adventure of exploring the cosmos, is learning to accept that. Learning to be okay with the fact that reality is stranger than we imagined. Learning to find beauty and wonder not in comfortable answers, but in the challenge of pushing beyond our limitations. We are a species that evolved to throw spears and gather berries and avoid predators. And yet, somehow, we have managed to figure out that the universe is expanding, that it started in a hot, dense state 14 billion years ago, that it might be infinite and might go on forever. We've managed to measure the geometry of space itself. We've looked back in time to see the universe as it was when it was just a few 100,000 years old. We've cataloged hundreds of billions of galaxies and discovered thousands of planets around other stars. We've done all of this with brains that were never designed for the task. Brains that struggle with infinity, that can't visualize higher dimensions, that rebel against the idea of space expanding without expanding into something. And yet we persist. We ask questions. We build instruments. We develop theories. We test them. We refine them. We push the boundaries of human knowledge a little bit further every day. That's what makes us human. Not that we have all the answers, but that we keep asking the questions even when the answers are difficult or uncomfortable or counterintuitive. So, when you think about the universe expanding, when you try to wrap your head around what it's expanding into, remember that you're grappling with one of the deepest questions about the nature of reality. A question that challenged Einstein, that puzzled the greatest minds of the 20th century, that continues to fascinate physicists and cosmologists today. And the answer, strange as it is that the universe isn't expanding into anything. Because the universe is all there is. There's no outside, no void, no higher dimensional space waiting to be filled. Just space itself, infinite or finite, evolving and expanding according to the equations of general relativity. It's not the answer our intuition wants, but it's the answer the evidence gives us. And in the end, that's what matters. Not whether reality conforms to our expectations, but whether we have the courage to accept reality as it is, even when it defies everything we thought we knew. We've journeyed through the physics, the mathematics, the philosophy, and the cognitive limitations that shape our understanding of the universe and its expansion. We've established that the universe isn't expanding into anything because there is no outside, no boundary, no void beyond space itself. But I want to spend this final part exploring the implications of this answer. Not just what it means for our understanding of cosmology, but what it means for us as human beings living in this strange, infinite, ever-expanding cosmos. Because the question of what the universe is expanding into isn't really just a question about physics. It's a question about our place in reality. It's a question about meaning and purpose, and whether there are limits to what we can know and understand. Let's start with called the Copernican principle. The idea that we're not special, that our location and our time and our circumstances are typical rather than exceptional. And this principle has been a powerful guide in science. Whenever we're tempted to think we're special, the Copernican principle reminds us to check that assumption. Are we really special, or are we just assuming we're special because we're us? More often than not, we're not special. We're typical, average, unremarkable. Now, you might think this is depressing, and in a way, it is. It's hard not to feel a bit small and insignificant when you contemplate the scale of the universe. When you realize that our entire existence, all of human history, every person who's ever lived, every empire that's ever risen and fallen, every work of art ever created, all of it has happened on a tiny rock orbiting an ordinary star in an unremarkable galaxy, in a universe so vast that most of it will forever be beyond our reach. From the universe's perspective, we don't matter. We're a brief flicker, a momentary arrangement of atoms that will soon disperse back into the cosmos. In a few billion years, the sun will expand into a red giant and engulf the Earth. In trillions of years, all the stars will burn out, and the universe will be dark and cold. In an unimaginably long time, even the black holes will evaporate, and nothing will remain but a thin soup of particles spreading out through infinite space, getting more and more dilute, approaching but never quite reaching absolute zero. The universe doesn't care about us. It doesn't care about anything. It just is, expanding and evolving according to the impersonal laws of physics, indifferent to our hopes and fears and dreams. That's one way to look at it. But here's another perspective. Yes, we're small. Yes, we're insignificant on a cosmic scale, but we're also the universe becoming aware of itself. We're made of atoms that were forged in the cores of stars that lived and died billions of years ago. We're literally stardust, organized in such a way that we can look back at the stars and understand where we came from. We're the means by which the universe explores itself, questions itself, tries to figure out what it is and how it works. Out of the chaos of the Big Bang, Out of the random collisions of particles and the slow accumulation of matter into stars and planets, somehow, improbably, life emerged. And not just life, but consciousness, the ability to perceive, to think, to wonder, and not just consciousness, but self-consciousness, the ability to reflect on our own existence, to ask questions about our place in the cosmos, to seek meaning and understanding. This is extraordinary. This is miraculous in a non-religious sense. The universe is mostly empty space and radiation and dark matter. But in a tiny corner of one galaxy, on the surface of one planet, conditions were just right for atoms to organize themselves into structures capable of thought, capable of asking, what is the universe expanding into? And capable of figuring out the answer. We are, as far as we know, the only beings in the observable universe who can do this. There might be others out there, probably are others given the sheer number of planets, but we haven't found them yet. For now, as far as we can tell, we're it. We're the universe's way of understanding itself. And that's not insignificant. That's profound. Yes, we're small, but small things can be important. A single neuron in your brain is tiny, insignificant on its own. But connected to billions of other neurons, it becomes part of something much larger. A mind, consciousness, the ability to experience the world. Similarly, we might be tiny parts of a vast cosmos, but we're parts that can think and feel and wonder, and that gives us meaning, even if the universe as a whole has no purpose. We create our own meaning. We decide what matters. And one of the things that matters, one of the things that drives us as a species, is the desire to understand, to push back the boundaries of ignorance and see what's really out there. This brings us to a question that's been lurking in the background of this entire discussion. Are there limits to what we can know? Are there questions that are forever beyond our ability to answer? The universe is expanding, and that expansion is accelerating. As we discussed earlier, this means that galaxies beyond our cosmic horizon are receding faster than light. We can never catch up to them. We can never see them. They're permanently beyond our reach. As the universe continues to expand, more and more galaxies will cross this horizon and disappear from view. In the far future, observers in the Milky Way will look out and see almost nothing. Just the handful of galaxies in our local group, gravitationally bound together. Everything else will be gone, carried away by the expansion. But it's worse than that. The cosmic microwave background, that afterglow of the Big Bang that's been so crucial to our understanding of the early universe, is also fading. It's being redshifted by the expansion, stretched to longer and longer wavelengths. Eventually, it will be redshifted into oblivion, completely undetectable. Future cosmologists, billions of years from now, won't have access to this crucial piece of evidence. They won't be able to see the early universe. They won't be able to detect the expansion because all the distant galaxies will have disappeared beyond the horizon. If they try to do cosmology, they'll conclude they live in a static universe consisting of just a few galaxies surrounded by empty space. They'll be completely wrong, but they'll have no way to know it. All the evidence will have literally moved beyond their reach. This is deeply unsettling. It suggests that our understanding of the universe is contingent on when and where we happen to exist. We're lucky to be living at a time when we can still see the cosmic microwave background, when we can still observe distant galaxies and measure the expansion. If we'd evolved a few billion years later, we might never have figured out the Big Bang. we might never have discovered that the universe is expanding. We'd be stuck with a fundamentally incorrect picture of reality, and we'd have no way to know we were wrong. This raises an obvious question. What are we missing now? What crucial pieces of evidence have already slipped beyond our horizon? What features of the universe existed in the past, or will exist in the future, that we'll never be able to detect because we happen to exist at this particular moment in cosmic history? We have no way to know. By definition, if something is beyond our observational reach, we can't observe it. We might be able to infer it indirectly through its effects on things we can observe. But there might be aspects of reality that leave no observable trace, that have no effect on anything within our cosmic horizon. And if so, we'll never know about them. This is the horizon problem in a broader sense. Not just the question of how distant regions of the early universe reached the same temperature, but the fundamental limitation that we can only see a finite portion of what might be an infinite universe. We're inside a bubble, our observable universe, and we can never see beyond it. This has profound implications for the question we've been exploring. What is the universe expanding into? Because even if there is something outside our universe, even if our universe is a bubble in a larger multiverse, we can never observe that larger structure. It's forever beyond our horizon. So, in a practical sense, it doesn't matter. The universe we can observe, the universe we can interact with, is all there is for us. Anything beyond that might as well not exist, at least from our perspective. This is a kind of cosmic solipsism. We can only ever know about the things we can observe, directly or indirectly. And the set of things we can observe is fundamentally limited by the speed of light and the age and expansion rate of the universe. There might be an infinite amount of universe out there that we'll never see, or there might be nothing beyond our horizon. From our perspective, it makes no difference. This is frustrating for anyone who values truth and understanding. We want to know the full picture. We want to understand reality as it actually is, not just the small slice of it we happen to have access to. But we might not have that option. Reality might be fundamentally larger than our ability to observe it. And we have to make peace with that. We have to accept that there are questions we might never be able to answer, not because we're not smart enough, or because our technology isn't advanced enough, but because the answers are fundamentally beyond our cosmic horizon. But here's the thing. Even within our limitations, we've accomplished something remarkable. We've figured out that the universe is expanding. We've traced that expansion back to the Big Bang. We've measured the age of the universe, the density of matter and energy, the geometry of space. We've tested our theories against observations and found them to be accurate to a staggering degree. We've built a coherent picture of cosmic history, from the first fraction of a second after the Big Bang to the present day. And we've done all of this with instruments that can only observe a tiny fraction of the electromagnetic spectrum, from a single planet orbiting a single star. We're like people who've spent their entire lives in a windowless room, and yet we've managed to deduce the existence of the building around us, the city outside, the planet we're on, the star we orbit, and the universe beyond. We've done this through careful observation, logical reasoning, mathematical modeling, and relentless curiosity. And while there might be limits to what we can know, we haven't hit those limits yet. We keep finding new ways to probe deeper, to see farther, to understand more. Every generation of telescopes reveals things the previous generation never imagined. Every new particle accelerator pushes the boundaries of our understanding of fundamental physics. We don't know where the limits are. We don't know what we'll discover next. And that's exciting. That's what drives science forward. Not the comfortable certainty of having all the answers, but the exhilarating uncertainty of not knowing what we'll find when we look a little deeper. Let's come back to the original question one more time. What is the universe expanding into? We've established, as firmly as current physics allows, that the answer is nothing. The universe isn't expanding into anything. There's no outside, no void, no pre-existing space. The universe is all of space, and space itself is expanding. But I want to suggest that the real value of this question isn't in the answer. It's in the journey of trying to answer it. Because in grappling with this question, we've had to confront some of the deepest mysteries of existence. What is space? What is time? What does it mean for something to begin? Can infinity change? These aren't just physics questions. They're philosophical questions. They're questions about the nature of reality itself. And in trying to answer them, we've developed new mathematics, new theories, new ways of thinking about the universe. We've built instruments that can see back to the dawn of time. We've sent probes to the edge of the solar system. We've detected gravitational waves, ripples in space-time itself, confirming predictions Einstein made a century ago. The question of what the universe is expanding into has led us on a journey of discovery that's expanded our understanding of reality in ways that would have been unimaginable 100 years ago. And that journey isn't over. There are still mysteries. What is dark matter? What is dark energy? What happened at the exact moment of the Big Bang? Is the multiverse real? Do we live in an infinite universe or a finite one? What lies beyond our cosmic horizon? We don't know the answers to these questions yet, but we're working on them. Physicists and cosmologists around the world are building new experiments, developing new theories, making new observations. Each discovery opens up new questions, and the frontier of human knowledge keeps expanding, much like the universe itself. And here's something beautiful. You're part of this. By asking questions about the universe, by trying to understand how it works, by reading about cosmology and astronomy and physics, you are participating in humanity's collective effort to make sense of reality. You're part of the process by which the universe comes to understand itself. It doesn't matter if you're a professional physicist or just someone curious about the cosmos. The act of asking questions, of seeking understanding, of refusing to accept simple answers when the truth is more complex, that's what pushes us forward. That's what makes us human. So, when you think about the universe expanding, when you try to visualize what it's expanding into and find yourself frustrated by the answer, don't be discouraged. That frustration is a sign that you're thinking deeply about something profound. You're pushing against the limits of human intuition and trying to grasp something that no brain evolved to understand. And even if you never fully internalize it, even if it never quite clicks into place emotionally, you can still appreciate the journey. You can still marvel at the fact that we've come this far, that we've gone from thinking the Earth is flat and the stars are holes in a celestial sphere, to understanding that we live in a possibly infinite universe that began 14 billion years ago in a hot, dense state, and has been expanding ever since. That's an incredible achievement. That's something to be proud of as a species. We're far from perfect. We still fight wars. We still struggle with inequality and injustice and environmental destruction. We still have so much work to do to make this world a better place for everyone who lives on it. But we're also capable of extraordinary things. we're capable of looking up at the night sky and figuring out what those points of light are. We're capable of building machines that can detect the afterglow of the Big Bang. We're capable of asking what the universe is expanding into, and then working through the physics and mathematics to understand why that question is based on a flawed premise. We contain multitudes, as Walt Whitman said. We're capable of great cruelty and great kindness, profound ignorance and profound wisdom. We're complicated, contradictory, flawed beings living on a small planet in a vast cosmos. And yet we keep asking questions. We keep seeking answers. We keep trying to understand. And maybe that's enough. Maybe that's what gives our lives meaning in a universe that has no inherent purpose. We create purpose through our curiosity, through our desire to understand, through our refusal to accept ignorance when knowledge is within reach. The universe isn't expanding into anything, but our understanding of the universe keeps expanding. And as long as we keep asking questions, as long as we keep seeking answers, as long as we keep pushing against the boundaries of what we know, we're fulfilling something essential to what it means to be human. We're exploring, we're discovering, we're learning. And in doing so, we're making the universe a more interesting place, at least from our perspective. Because without consciousness, without minds to observe and understand, the universe would just be particles and fields evolving according to physical laws. Beautiful, perhaps, in an abstract sense, but meaningless. It's consciousness that gives things meaning. It's minds that can appreciate beauty, that can find wonder in the cosmos, that can ask why and how and what if. And we're those minds. We're the ones asking the questions. We're the ones seeking the answers. And even though we're small and temporary and insignificant on a cosmic scale, we're still here. We still matter, at least to each other, and we're still curious. So the next time you look up at the night sky, the next time you see those distant points of light and think about the vast gulfs of space between them, the next time you contemplate the expansion of the universe and wonder what it's expanding into, remember this: you're part of something extraordinary. You're part of the universe's attempt to understand itself. You're made of atoms that were forged in stars, and those atoms have organized themselves into a structure capable of looking back at the stars and asking where they came from. You're a temporary arrangement of matter and energy that, against all odds, can think and feel and wonder. And that's not nothing. That's everything. The universe isn't expanding into anything because the universe is everything. All of space, all of time, all of matter and energy. And you're part of it. You're a small part, yes, but you're still part of the greatest story ever told. The story of how the cosmos came to be, how it evolved from a hot, dense state into the rich tapestry of stars and galaxies we see today, and how, in at least one small corner, it gave rise to beings capable of appreciating it. That's a story worth telling. That's a story worth learning. And that's why we ask questions like, what is the universe expanding into, even when the answer challenges everything we thought we understood. Because the journey of discovery is what makes us human. And as long as we keep taking that journey, as long as we keep asking questions and seeking answers, we'll continue to expand our understanding of this strange, beautiful, infinite cosmos we call home.